Alright, so section 3.4, the chain rule. Okay, the chain rule. This is the definition of the chain rule. I'm going to ask a volunteer to read the entire top part on this page. Dylan?
The chain rule. If f and g are both differentiable and f equals f of g is the composite function defined by f of x equals f of g of x,
Yes.
then f is differentiable and f prime is given by the product f prime of x equals f prime g of x times g prime of x.
Leibniz.
If in Leibniz notation, if y equals f of u and u equals g of x are both differentiable functions, then dy over dx equals dy over du times du over dx.
Very good. Very good. Okay. So chain rule. Okay. When do we use chain rule to do the derivatives? If our given function capital F of x is a combination function or composite function. Okay. So capital F of x is defined by lowercase f of g lowercase g of x. So this function we called it is what? Composite function f composite g. Do you still remember we did this in section chapter 1? Okay. So if capital F of x is a composite function of f composite g and can be written by f of g of x. So there are two functions, okay? G is closer to x, so we call G is an inner function, and then f is like a little bit further away, we call f is an outer function, okay? So if this is the case, then to differentiate capital F, okay, so it says capital F is differentiable, okay? So f prime, okay, the derivative of capital F is given by a product, okay? What product? The first factor in the product is what? The derivative of the outer function f. Okay? And then the second factor in the product is the derivative of the inner function, g. Okay? So we can tell that the derivative of the composite function is a product of differentiations from both of the outer function f and the inner function g. Right? However, for the inner function g is a function of variable x only. So we only compute the derivative of g of x. Okay, g's of x. But because function f, it is a function of g of x. So when we differentiate the f, we have to make sure it is a derivative of f at g of x. Okay, so it is a product of f and g. Okay, and for f, it is the derivative of f at g of x. Okay, alright, so this is the idea for the chain rule. Okay, in the Leibniz notation, okay, if y is a function of u, okay, y equals f of u, okay, y is a function of u, okay, u is a function of what? X. Okay, so this is what? This is y equals f of what? What is u? G of x. So it's the same thing as a capital F. It's the same thing, okay? So y is a function of u is a function of x. Okay, both of these two functions are differentiable. Then dy over dx. We want to differentiate y with respect to x. Okay, how to do it? We're going to differentiate y with respect to what? U. Okay, and then differentiate u with respect to what? X. Okay, so dy over du, what is this? This f prime of x. Okay, dy over du, it is the derivative of f. Bless you.
Thank you.
And then what is du over dx? Du over dx, it is a derivative of what? G with respect to x. Okay, see, Leibniz notation is just using a different notation to describe the chain rule, but are they the same? They are equivalent. You see, dy over dx, it is a derivative of y with respect to x, okay? And then it's defined by what? A product. What kind of product? dy over du is the derivative of the outer function, which is f prime of x. Du over dx is a derivative of what? Inner function g. So they are the same thing, just different notation. Do you see that, everyone? Alright, so example. We're going to differentiate, okay? We have question A, B, and C, okay? So I will see that I'm going to pick up some questions to do, okay? We have question A, B, and C. Let's pick up two to do together. Which one do you want to try? A and C? Can we do A and C? Okay, let's do A and C, okay? Later you're going to try B, and I'll show you the answer, okay? So, differentiate y equals sin of x squared. What is independent variable? X. What is dependent variable? Y, right? So, differentiate y with respect to x, okay? So this is our capital F, right? Capital F. Now, my question for you is, sin of x squared, if we consider this function is a composite function, which function is f? Which function is g? Sin of x squared.
Sin of x squared is g.
Yeah. X squared we let it to be what? G. And then f is what? Sin. Right? Same function. Right? Do you see that, everybody? Do you see that? Because this is the inner one, right? X squared is the inner function, sin of function is the outer function, this is the f, okay? So, the derivative of y equals what? Product of the derivative of f of g of x, okay? So, f, what is the derivative of the same function? Cosine, right? So it is going to be cosine of what? Of g of x. What is g of x? X squared. And then times by the derivative of g, right? What is g's derivative? What is x squared's derivative? 2x. Okay, or you can write 2x times cosine of x squared. The reason why we write the 2x in front of the cosine is because I don't want you guys to have an impression about this is cosine of x squared times by 2x. No, it is 2x times by cosine of x squared, okay? You guys? It makes sense? Okay, so this is by the regular definition chain rule. Can we use Leibniz notation to do the differentiation?
Be a bit more annoying, yeah.
Yeah, so we need to define what is what? Lowercase f, what is lowercase g, right? So, by using, okay, if this is method 1, okay, I'm going to write it here. I just want to let you to experience by either this way or the Leibniz notation way. But when you do the calculation, you don't have to do both. You don't have to, you just need to pick up one. Okay, so method 2, okay, Leibniz notation. Leibniz notation. By using Leibniz notation, we need to know function f and the function g, right? So we let y equals what? F of u, right? Sin of u, okay? And u is what? U is what? X squared, right? Do you see that, right? Y equals sin of u, and u equals what? G squared, right? X squared, right? Right, guys? This is y equals sin of x squared, right? It's the same thing as this, right? So we just need to let u equal g of x, which is x squared, and then what? Yeah, so this is g of x, okay, this is g of x, x squared, and y equals sin of u. Alright, by Leibniz notation, compute dy over dx. It is going to be a product of what? Dy over du. What is dy over du? Sin u's derivative with respect to u is what?
Cosine.
Cosine u. And times by du over dx means what? The derivative of u with respect to g give us what? 2x, right? But can we say our answer is cosine u times by 2x? Can we say that way? No. Because this function, it is a function of y with respect to x. So the derivative of y with respect to, the derivative of y with respect to x must be a solution with x only, okay? A function of x only. So we have a cosine u here. What do? Because u equals what? X squared. So we say cosine u is cosine x squared times by what? 2x. And what is this? 2x times by cosine of what? X squared. Let's compare the conclusion. Are they the same? Yes or no? Yes.
You can really tell Leibniz was German.
German?
Yeah, Leibniz, the mathematician.
Oh, he's German, right?
Yeah, I'm just saying only a German could come up with a system that contrived.
Okay. So, I'm really clear about those methods. Well, if you're clear with, the idea for chain rule, you don't have to do this fancy. Sin function is outer function, we differentiate that, give us cosine of whatever is in the inner function. And then times that what? Derivative of the inner function. That's it. Okay? So this is what? This is the idea for differentiate this function y. Can we move on to C?
Yes.
Alright, for C, I'm going to ask you, how many layers of functions do we have in this question? From this previous function, how many layers? 2 layers, right? We have a function g, we have a function f, right? The inner function is x squared, outer function is what? Same function. Now for this question C, let's check the layers of the functions. Y equals same of square root of 1 plus x squared.
There's 3.
What? 3 layers. What are the 3 layers? Same function is an outer one, right? This is the most far away from x, right? Then what is the second layer? Can you tell? Square root, right? What is the most inner one? 1 plus x squared. Can we consider it is 3 layers? Can we?
So you have to do it 3 times?
We have to do a product of 3 derivatives. Depends on how many layers of function. Either 2 layers, 2 factors from the product. If there are 3 layers, we have to compute a product of 1, 2, 3 factors. Okay, let's try. Y prime equals. We always start from the outer function. Okay, outer function. Sin of square root of whatever. What is the derivative of same function? Cosine. Okay. Cosine of what? Cosine of whatever is remaining. Okay. This is not product, okay? This is cosine of. Okay, sorry. I don't want to mean that it's a cosine times, okay? It is cosine of square root of 1 plus x squared. Okay? Then, guys, what do? We're going to consider this is the inner function right now. It's not a, the 3 layers, okay? Cosine of whatever this, okay? But we have to compute what? The derivative of whatever is left. What do you think? So consider this is the 2 layers right now. Okay, eventually you'll see three factors in the product, okay? But right now, let's consider same function is the outer one, everything else is the inner one. So by using the chain rule, it is going to be a product of derivative of the same function, which is cosine of whatever left, times by whatever left derivative, right? Do you see that? So far only two factors, okay? Now, cosine of square root of 1 plus x squared, we cannot do anything further for that factor, which is leave it there. Let's compute the square root of 1 plus x squared. We need to find the derivative of this part. As we talked about, square root is the outer function, right? 1 plus x squared is what? Inner function. So how to differentiate a square root function? Do you still remember? I let you guys remember that. Square root of x equals, remember this, 1 over what? 2 times square root of x. Remember this, right? Because you don't want to do it every time. Oh, what is the square root of x? This equals x to the 1/2. By using the power rule, you can get this conclusion, but
Can we put that on a formula sheet or that in this?
yes! You can put it on a formula sheet. Square root of x,
So it's just gonna be
yeah. So,
1 over 2 times
Yes.
the square root of 1 plus x squared.
very good. We have a square root of 1 plus x squared. Now, by using this conclusion, okay, it's going to be 1 over 2 times square root of whatever left, 1 plus x squared. But,
And that's the derivative of the square root of x, right? Not just the x, the square root of x, right?
this is a derivative of the square root, because this is an outer function for this derivative. So we have to compute the derivative of the outer function of 1 plus x squared. Then times by what? This most inner function's derivative. You see? Now let's check how many factors. 1, 2, and what? 3. Okay. Of course, we're not done yet because we haven't done 1 plus x squared derivative yet. But we have one more step. What is that one more step? Cosine of what? Square root of 1 plus x squared times by what? 1 over 2 square root of 1 plus x squared times by 1 plus x squared derivative with respect to x. What should we have? 2x. Why? Because y is constant is 0. X squared derivative is what? 2x. Okay. Yeah, we can consider this 2x over 1. Can we simplify, everyone? See, 1, 2, 3, 3 product. Okay. Yeah. Well, 3 factors in the product. 2, 2 cancel out. Okay. So this x you can write it is on the top of this fraction. Okay. So you can combine. Okay. I'm gonna write one more step. Okay. So conclusion is x over square root of 1 plus x squared times by cosine of what? Square root of 1 plus x squared. Woo. This is the most simplified. Well, this is not the most simplified, but this is already simplified, good enough for us, okay? You see, oh, there is square root on the bottom. You can leave it there, okay? It doesn't say you have to make sure it's a, most reduced form, okay? So this is already good enough, okay? What's up?
In class, we could have like 5 minutes to spend together trying to think what we should put on our formula sheet.
Yeah.
I'm a little lost.
Yeah, that's fine, that's fine.
Not with the material, the lost is what we put down. Right?
Okay, yeah. Yes, we can do that. So that's good, everybody? Okay? Well, we really have to practice, okay? We really have to practice, okay? Well, the idea for the chain rule is what? Depends on how many layers of the functions, how many layers in the composite functions, okay? So this is 2 layers, f and g, okay? So if I'm going to write f is a composite function of g, f and g, and simple example h, okay? So how do you compute the derivative of capital F? It is going to be what? F's derivative times the derivative of g times the derivative of what? H. Okay? So because h is the most inner one, so it will be only the derivative of itself, h. But g is a function of h. Okay? So because this is f of g of h of x. Woo. 3 parentheses, right? You can write this down on the side of your notes or on your book or anywhere, okay? If this function is a composite function of 3 layers, what do? Eventually, our answer will be a product of 3 factors. Each factor is a derivative for that function, okay? So, derivative of h, derivative of g, but is derivative of g of h of x. This derivative of f is going to be what? G of h of x. So that means when we start to differentiate, we always start from the outer function f. But make sure that once we differentiate f, we have to keep everything. Okay, we have to keep the rest part from the function. Then times by the other function derivative and keeps whatever is left, and then eventually times by what? The most innermost function's derivative, only in terms of x. Yeah, this is like a summarize from the question we have just done, okay, from the thing of square root of 1 plus x bar. Do you see that?
Are we ever going to do anything more than 3?
I don't think so.
No.
3 layers, enough. Very rarely you will have more than 3, but 3 already enough.
Okay.
Alright, guys, do you have a brief idea about how to do the chain rule? Okay. Alright, so this is a chain rule, okay? In general, okay, in general. Now let's look at power rule combined with the chain rule. Okay, power combined with chain rule. I'm going to ask volunteer to read this conclusion for us. Dave?
The power rule combined with the chain rule. If n is any real number and u equals g of x is differentiable, then d over d of x to u to the nth power is equal to n times u to the n minus 1th power to du over d of x.
Okay.
Alternatively, d over d of x to the g of x to the nth power equals n to the g of x to the n minus 1th power times g prime of x.
Okay, thanks. Okay, so power rule combined with chain rule. Okay, so that means, when I use power rule, okay, everybody know how to do power rule, right? X to the nth power is derivative equals n times by x to the n minus 1th power. Now, this u is a function of g. Okay, so to differentiate u to the nth power, first we're going to use power rule to get n times u to the n minus 1th power. Then we times what? Du over dx. Okay? Or if we write u explicitly as g of x. So the derivative of g of x to the nth power, okay, by using the power rule will give us n times g of x to the n minus 1th power. But we also have to multiply by what? The derivative of g. Okay? This is by using a kind of Leibniz notation. This is like, well, they are the same thing. Okay? Just one use, u equals g of x. The other one is write out g as u as g explicitly. Okay? So they are the same, right? See, power rule times by the other derivative. Right? All right. So we have 1, 2, 3 questions, okay? So, from question A, think about it. B and C, pick 2, we'll do them together. A and C? A and C, okay. Alright, A and C. Sure. Okay. I'm going to pause the video and then restart it, okay?